Thank you very much, Giovanni, and I'd like to thank all the organizers for giving me the opportunity to speak to you today. I'd like to describe our work using a diamond-based magnetic microscope to study magnetic materials, and particularly chiral-induced magnetization and Van-der-Waals magnets. So I'll start with a brief intro into the NV system for those of you who are less familiar. We're talking about the nitrogen vacancy localized atomic defect within diamonds. So this is kind of a cartoon of the diamond crystal structure with the blue circles depicting carbon atoms, and the substitutional nitrogen and nearby vacancy comprising the NV defect. And this defect is kind of has gained traction over the past several years as a useful system for various types of research. But in our context, it could be a kind of a nice platform for magnetic microscopy, in the sense that it's, first of all, it's a solid state system. It's essentially uses with NVs incorporated near the top surface. And these NVs have long coherence times for their spin degree of freedom. So they have a ground state spin triplet, as you can see in the schematic energy diagram shown here. And these long coherence times translate into relatively good magnetic field sensitivity for the measurements that we'd like to perform. And finally, the word microscopy kind of suggests that we have the advantage of optically addressing these defects, and importantly, we can get information on the spin properties of these defects optically. And that's kind of a useful property that allows us to build up a system that essentially looks like what you see in the cartoon on the left. We basically build an optical microscope, an optical fluorescence microscope, in which we shine green light on our diamond slab with the NVs near the surface, and then we collect the fluorescence coming out of these NVs onto a camera, so that we can essentially image the fluorescence coming out of these NVs. We incorporate into this microscope the capability of applying a static field, static magnetic field through Helmholtz coils and microwave antennas, so that we can drive the transitions of these NV spins. And using that combination, we can essentially translate the intensity, the fluorescence intensity image that we obtain on the camera into a magnetic field image. And the idea behind it is shown on this plot here to the right, where we essentially, for each pixel on the camera, for each spatial location, we scan the frequency of applied microwave and observe the resonances that correspond to the spin transitions of NVs within the diamond crystal along different possible orientations. So we end up getting this this type of picture containing 8 different resonances, and from the frequency position, from the spectral position of these resonances, we can extract the magnetic field that the NVs are feeling, are subject to at that pixel. So we essentially can translate this type of system into an optical magnetic microscope, providing spatial resolution that's optically limited, basically submicron resolution limited by the diffraction limit, along with relatively good magnetic field sensitivity, which in some sense also depends on how far the sample that we put on top of the diamond is from these NVs that are sensing the magnetic field. But the scale of sensitivity that we obtain normally is around a few hundred nanotesla per square root hertz. And this tool can now be applied in various directions. And just as an example, kind of very briefly flashing some directions, we're working on measuring 2D materials. I'll show you some of the preliminary 2D magnet work that we've done, but we're also imaging currents in corresponding transport effects in various materials. We've been looking at magnetic nanoparticles in the context of paleomagnetometry of these magnetic particles within minerals, and also non-static sort of AC measurements that can be related to NMR or to EPR or to other related fields. So this is my brief intro into the subject, and now let me mention that I'd like to, if I make it, I'd like to cover a couple of recent results that we've been able to measure using the system. One is the reorientation of magnetization in a thin layer magnet using chiral structures or chiral molecules in this case, and also the measurement of the magnetic structure within thin or Van-der-Waals magnets, in this case FEGT. And then I'll summarize. Okay, so let me start briefly with introducing the topic of chiral molecules or chiral-induced magnetization. And I'm guessing that that most of you are familiar with chirality in nature, and specifically chiral molecules that are quite common and are encountered kind of ubiquitously in chemistry and biology. There's a kind of a very famous story about kind of how we've come to learn about the importance of chirality, specifically in the context of drugs and medicine, and that's the relatively sad case of phthalomid, which was administered to pregnant women without knowing that a certain chirality of it can be detrimental to the health of women and their embryos. And this drug was actually banned or was not approved in the US because this FDA official, Francis Kelsey, was insisting on good practice of drug companies to produce clinical tests and provide the results, and was kind of a nice. She got some medal from Kennedy, and it was also a sort of motivation for strict rules employed by FDA to this day. And maybe it's important for us to wait a little bit with vaccines and stuff till they finish all the measurements and what's going on today. So another effect that has been identified over the past several years is an effect that's related to spin transport along chiral structures, and specifically chiral molecules, and that is the chiral-induced spin selectivity effect, in which there's transport dependence on the spin of the electrons passing through such a chiral structure, such a chiral molecule, and essentially there's a resulting spin filtering effect in which a certain spin of the electron is allowed to or passes through efficiently through such a structure, as opposed to the reverse spin, and that is of a kind of a interesting and not perfectly well understood effect that has been demonstrated many times over the past several years, but is at least conceptually in a hand waving explanation can be understood through an effective magnetic field or an effective spin orbit coupling that's induced by this by the chiral structure of the molecule, which then creates an energy split between these two spin states, allowing one spin state to travel across or to transport across the molecule, while the other one is suppressed. In addition, to this transport effect, to the filtering of spin due to the chiral structure, it has been realized that the chirality of the structure of these molecules can affect magnetic layers. And an example of this was shown a few years ago in the group of Yossi Paltiel, where a thin cobalt layer, 18 angstroms, which is capped by gold, was then subjected to the adsorption of chiral molecules in specific regions. So there was selective adsorption of molecules on the surface of the sample, and then the magnetization was measured using AFM and FM, so topography and magnetization, and one can see that these regions in which the molecules were adsorbed show clear topography, an AFM image showing this monolayer of chiral molecules adsorbed on the surface. The difference between these two pictures is the handedness of the molecules. So these are reverse handedness molecules, but the topography is the same. But a similar MFM image, magnetic image, shows the opposite magnetization induced within the sample due to the handedness of this of the chiral molecules adsorbed on top. And I'd like to stress that this result is a steady state result that does not require any current or any transport happening. So the molecules are essentially just adsorbed on the surface, and then the magnetization is subsequently measured as shown here. So this result was measured a few years ago, and while the effect is clear, it's not fully understood how this actually happens, and we might actually state a few open questions that are kind of remain in this context. And maybe an important one is whether this effect this magnetization reorientation effect is persistent or transient, in the sense that perhaps this is an effect related to charge redistribution during the adsorption process. So it's a transient effect occurring during this chemical adsorption of the molecules on the surface, potentially suggesting that it's related to strong exchange interactions on the surface, and then it would be persistent over a long period of time. And then following these open questions, there are questions related to magnitude and direction of the magnetization, and how this changes over time. And for all of these questions, we introduced our diamond magnetic microscope, which allows us to perform quantitative vectorial magnetic measurements that could be useful in answering or addressing these questions. Let me just mention that actually following our preliminary results, there have been also other experiments performed in other groups, and specifically SDM performed by Christoph Tegenkamp have shown that the specific molecules that we've been using, the alpha helix polyalanine molecules, they adsorb on the gold surface at an angle that's approximately 45 or 50 degrees to the surface normal. And that, as you'll see in a second, that kind of relates to what we're showing before. Prior to our results and to these recent measurements by the Tegenkamp group, we were unaware of this tilt angle, and we had this notion that the adsorption was perpendicular to the surface. So what we were doing, or basically the results that I'm showing here, are essentially measurements performed using this magnetic microscope, depicting a spatial image of the stray field created by the sample and measured by these NVs. So you can see that we can get approximately micron spatial resolution of measuring the magnetic field created by this thin layer of cobalt. So this is an example of the measured stray field, and now we can use such a measurement. Maybe I should point out that we're using very similar samples to the one I've showed in the previous experiments. So we selectively adsorb chiral molecules on the sample surface, but we place the sample at a standoff distance of approximately 10 microns from the NVs, from the diamond, such that what we're measuring is an effective dipole field emanating from these structures. So if we look at the stray field that we measure, we can now compare it to a simulation of the magnetic field emanating from that structure created by the selective adsorption of chiral molecules. And this is the simulated field. I'm presenting here the field along the z direction, which is perpendicular to the sample surface. So we can use such an analysis now to extract the dipole angles, the angles of the effective dipole of the magnetization in the sample, as well as the magnitude of the magnetization. So we use the fact that we are well into the dipole approximation to allow us to use the simulations and extract information about magnetic field or magnetization amplitude and angle. In addition to that, we can perform these measurements as a function of time. And this is an example of the same type of measurements that I've shown previously, performed at 4-hour intervals. And one can kind of readily see that the signal seems to decay over time, suggesting that there's some time dynamics. There's some change in the magnetization that we're seeing over a scale of hours. So if we now understand these tools and the methods that we use for analysis, we can now perform these measurements and really try to extract quantitative values of magnetization and amplitude and angle as a function of time. And if we start with the short time behavior, here I'm plotting the measured stray fields in all 3 vectorial orientations. And by comparing these to the simulations, as I've shown earlier, we can see that the field amplitude that we're measuring is approximately 10 Gauss, which decreases over time, as we've seen before, on the scale of hours. But in addition to that, we can measure the angle of the effective dipole of the magnetization in the sample, and we see that it starts at around 50 or somewhere between 40 and 60 degrees, and it increases over time with respect to the normal. And we can see this in the long time behavior. This is a corresponding measurement following approximately 10 hours from adsorption. One can see that, again, we're depicting the stray magnetic field measurements on the 3 axes. One can see that the amplitude of the field has decreased by about a factor of 10. But in addition to that, the magnetization angle has increased to about 80 degrees. So essentially, if we start with a magnetization or an effective dipole that points at about 45 degrees or 50 degrees, it slowly falls down. Okay, so it slowly becomes in plane. Following these results, we've performed additional AFM measurements to measure the actual angle of the adsorbed molecules as a function of time. And you can see a plot of the magnetization angle here on the left, measured as I've described in the previous slides, along with a measure of the molecular tilt angle, also measured as a function of time using AFM. So essentially measuring the height of the monolayer as a function of time and extracting from that the tilt angle of the molecules. And one can see that although there's some quantitative discrepancies, one can see that in cases we measure a correspondence between the change of the magnetization angle in the cobalt layer in the magnet together with the tilt angle of the molecules. So essentially, this change in the stray field that we're seeing corresponds to the fact that as a function of time, these molecules are essentially falling down. They're essentially becoming almost parallel to the surface of the sample. And this is an important result in the sense that it indicates that the magnetization of the cobalt layer follows the axis of the chiral molecule over a long period of time, over the period of time of hours or even days. And therefore, it strongly suggests that this effect, that the magnetization effect that we're seeing is a persistent rather than transient effect. So kind of summarizing what I was saying so far, I think that the results that we've shown demonstrate that in this system, the molecules change orientation over time scale of hours, falling down to the surface, and corresponding to that, the magnetization of the sample follows suit, also changes orientation from out of and we believe that this suggests that there's a persistent effect going on here, not dominated by charge redistribution during the short adsorption process, but rather dominated by a relatively strong exchange interactions between the molecules and the surface. And of course, this is a nice indication, but there's a lot of additional experiments and measurements that we would like to perform, including studies of these effects as a function of the layer thickness, the types of the molecules, and their length, and hopefully, in addition to that, also try to study the spin dynamics and coherence in this type of structure as a function of time. So with this, I would like to wrap up the part relating to this chiral-induced magnetization, and I'd like to turn over to ongoing experiments on the measurement of Van-der-Waals magnets using the same diamond magnetic microscope. This microscope is relatively well suited for measuring the magnetization of thin layer magnets, and of course these materials are relatively novel and interesting, and there's questions that one can ask in terms of how their magnetization changes versus time in the context of effects of oxidation of such layers, thickness dependence, and encapsulation, which are important for various types of actual applications or for understanding the fundamental properties of these Van-der-Waals magnets. And in addition, how this magnetization changes over time, trying to capture the dynamics of domains and the magnetic phase transitions in such materials. And these types of measurements could potentially be addressed using this magnetic microscope. And what we've decided to work with currently, our experiment works at room temperature. We're building up a low temperature experiment. Right now it works at room temperature. So we've decided to work with iron germanium telluride, which is a room temperature 2D magnet. The bulk Curie temperature is approximately 310 Kelvin, and it has an out-of-plane anisotropy. And that allows us to try to measure the magnetic structures or the magnetization structure within these systems, with these flakes at room temperature. This material is a Van-der-Waals material that can be mechanically exfoliated. So in this work, which we do in collaboration with Hadar Steinberg's group, we exfoliate the flakes and dry transfer them onto the diamond sampled, which will be used for the measurement, and which is pre-patterned with markings to allow us to identify the different flakes. In this example, we can optically measure the different flakes and identify them for our experiments. And then placing them in the microscope, we can measure, as I kind of similarly to what I've been describing before, we can measure the stray magnetic field vectorially to extract the magnetization information. And here we can see this stray field measurement, and we can see how we can essentially depict the magnetization in this flake through sort of a triangular dipole shape in the magnetization. And one can corroborate this by performing, again, dipole-like simulations of the stray field. One can see a relatively, at least a qualitative, if not quantitative, agreement. And I'll just flip it back for a second, and you can see how these simulations correspond to the measured field. We then do these measurements again as a function of time, and we again observe a decay of the actual field as a function of time. So the field structure remains relatively stable, but the magnitude of the stray field decays, and that seems to be consistent with oxidation of the flake. And we can see an optical measurement of how the flake oxidizes over time. And even though this is preliminary, and I wouldn't want to say anything definitive, but it seems that there's some correspondence between these two effects. So these are our preliminary results. We want to continue on by performing high-resolution magnetic measurements. These are MFM measurements along with AFM measurements of these flakes depicting magnetic domains. So what we want to do now is we want to extend our measurements to observe the magnetization as a function of temperature across the phase transition, which for bulk occurs at 310 Kelvin. For these flakes, it's not very, very different. And to see whether we can identify domain structure and magnetic fluctuations across this transition. Of course, we would like to continue studying the magnetization characteristics of these flakes as a function of their thickness, as well as various encapsulation techniques. So I don't know how I'm doing with time. I hope I'm okay. I've pretty much finished, so I'd like to just basically summarize by saying I hope I've shown you a nice tool for imaging magnetic structures and demonstrated how this could be useful in understanding the behavior of chiral structures coupled to thin magnetic layers and to these nice Van-der-Waals magnets. There's a lot of other things that one can do with the system, but for now, let me and done all the work that you've actually seen. So it's my students done Mirzada, Gali Chaim, Sarab Sinj, and Yechel Ben Shalom, my collaborators in funding, and I'd like to thank you for your attention.